Now, I'm going to stop this one and I'm going to go to the other presentation. Please, if you have questions, please ask me. And I'll do this one, a window and PowerPoint and share. Okay, so the work that I'm presenting is from my PhD student. Currently, he's in Lahore, in Pakistan. He's associate professor. His name is Qasim Khan. I'm going to present the work that he did within about 4 years. So in his PhD candidateship, in his PhD studies, the amount of work that he did, I'm going to show you the work, the amount of work. In a nutshell, there is a main thrust of the thesis, which I'm going to present to you. Then I'll show you how a good student can come up with different shoots. Like you have a tree, there is the main trunk, and then there are shoots, and there are other things. So he published his main experimental program. Then he was able to publish other papers which are not from the main thrust of the thesis, not from the main branch. They are from the sides. This indicates to me that he is a top PhD student. So the supervisor is Professor Sheikh. So we work together, and it doesn't matter who is the first supervisor. There are duties that we have over the years. So for example, thesis, I take care of the thesis fully. For papers, I read the paper first, then he reads it, then I read it again, then I submit. So there are some revisions when it comes to revisions of journals, the other way around. He looks after them, then I read at the end and I submit. So there are the roles are very clear. I do this, he does that. So it is very clear. The main thrust of the work of Qasim, or Professor Khan, was to use FRP tubes in concrete columns. So the main thrust is this. Okay, why FRP? Because of corrosion. So I told you we have a bridge. Whenever there is water, marine, salt, there may be corrosion. So this is the reason we are going to use different materials. So the different materials is, in this case, FRP tube. So Qasim came up with this idea. So as I said, I believe that the best material is reinforced concrete, steel reinforced concrete. But if there is areas like Wollongong, like Sydney, near the water, near the marine, then we go to these materials. So there are three parts in this presentation, and you will see the three parts, and you can see how we go about it. So FRP, fiber reinforced polymer, it is good material, it is strong in tension, it is light, it is not electromagnetic, it doesn't corrode. Admittedly, it is brittle, right? But steel, the tensile strength of steel is 500 MPa. whereas the tensile strength of FRP, GFRP 800, where it is CFRP, it goes to 1500 or more MPa. So FRP, yes, it is brittle material, but the strength is much higher. So if you use a proper design, then we can come up with proper design. So believe it or not, in 1928, a gentleman called Richard, not Richard, Richard with a T, he came up with this equation. And I always tell my students, the main thing in civil engineering, sigma fx, sigma fy, sigma moment, these are zero. So if you take sigma fy is equal to 0 and you sum, you will see that the confinement in the stress in the tube will be applied on the concrete. Of course, this is based on Poisson's effect. And we have all this idea in the on the right hand side, the curves, you can see if we have confined concrete, this is the behavior. In effect, you are changing the, if it is unconfined, it is axial, uniaxial loading. But if it is confined, it changes from uniaxial to triaxial. So due to Poisson's effect, you have higher strength. And there is this relationship between the confinement ratio and strain reduction. So it is the relationship between the FL, which is the confinement stress, over the compressive strength of concrete. This comes from that equation, which is just sigma Fy is equal to 0. And then you have the strain, rupture strain, divided by the ultimate strain of this is called strain reduction factor. So FRP, there are advantages: high tensile strength, high corrosion resistance, durable material, and actually mechanical engineers have been using it before us. They used it for repair of aircraft. They use the FRP currently, one of the Boeings, it's mainly all FRP. And they use it in cars as well and in boats, fiberglass. Now, this FRP bars, ACI 440 in 2006 clearly said don't use FRP bars. But the current ACI 440 doesn't say use or don't use. It is just, it's silent about it. Canadian standard says, okay, you can use it, but you ignore the contribution of the FRP bars in columns. So in this case, you take only the 0.85 F prime C, which is the compressive strength of concrete, and you multiply it by the net area of concrete. And you ignore the effect, usually we have the AS FY or FSY, where, or FRP, AFRP, but in this case, we don't take it. Now, when Qasim started this work, we said, okay, FRP tubes, being a civil engineer, being a civil structural engineer, there is something called fire. And fire is a problem. So the bars, at least if you have beam column inside the members, FRP bars inside members, then there is cover. And this cover may protect the bar from fire for maybe 1 hour. Whereas if the FRP is outside, then if there is fire, then you will lose the material. So Qasim did some preliminary study, and then there was some additives, chemicals, lightweight concrete you can apply on the tube to reduce the effect of fire, to allow people to run away. So let's talk about, I'm going to start with experimental program, and you will see there are two types of, two components of this. So we had carbon FRP tubes, glass FRP tubes, glass FRP bars, and carbon FRP bars. So what we did, we have the material testing, which is the preliminary testing. Then we go to the main testing, and I'll show you what we did in the main testing. In the preliminary testing, we tested all those materials. And in the main one, we had the columns, and they were 812 millimeter height, 203 millimeter diameter. And this is carbon, and it is FRP, and it is filled with concrete, and it is tube. And then there is the other one, the reference, which is steel. So we had steel and we had the FRP. Now, material testing, we did some standard testing, and we had the bars, which are 9 millimeter and 15 millimeter and 15.8. So the 9 millimeter is carbon, 15 millimeter is carbon, and glass is 15.8. And this is compression. So we had them by themselves, and we wrapped them, and then we tested them. Because this is compression and these are fibers. So we thought if we wrap them to increase the integrity of the fibers. You can see the clear length of those is very small. The highest is 80 millimeters. The old systems have 3 inches. It is not a big deal. So we did those. Now, for the tension, it is a different story. You can see for the, for example, if you have the 15 millimeter, you have clear length of 600 mil. Then on top of that, there are the anchorage lengths. So for those, we built steel tubes, we put the bar, and then we bought expansive cement, and then we put them, leave them for 3 days, not longer, and test them. If it is longer, you will have problems. Now, I was telling you that there is the main experiments. Qasim came to, this work is based on ASTM. ASTM has up to 12 millimeters testing. They don't have for 15 millimeters. And Qasim did this test, and we wrote a paper, and we sent the paper, and we published it to ASTM. This is not his main, this is not his main test. This is not his main program, but he was able to publish a paper in ASTM saying, adding to the standard. So these are the tests.